All right, welcome everybody to the beginning of a brand new week. And the background there is Violet Evergarden, of course, a outstanding anime that highly recommend if you're into anime. Really depressing, really good. So, what's crack lacking? So, all right, we are going to good news or bad news, depending on your perspective. Only about 15% of students completed the Shapes assignment, so I am not going to do a part 2 to it. So yay or boo, depends on your perspective. I always try new assignments every semester. Sometimes they work, sometimes they don't. So, whatever. Yeah, 15% completed the assignment. So there's always some AFK students that just like at some point just go and just stop showing up again, but still that's pretty low. And by complete, I mean got 100%. There was a number of people in the mid-tier range, thankfully. All right, so when it's already on the server, you can check your email there. You get your scores mailed on the server. Hey, it's coming. So we're going to start today with a warm-up assignment that will prep you for the next homework assignment. And the warm-up assignment is Min Corelli here. He took a photo of it. So he could show it to you guys. All right, in that case, let me just put it up on the screen here or something. All right, here is your warm-up assignment. Given in integers, print out the integers in the same order they were entered, but removing duplicates. Yep. One of my friends, former students' friends, is going to be applying to computer science jobs, so he's asking me to give him, programming interview question kinds of things. And so I would like to see you do this using the standard library. However, no, stood, unique, or similar function. There is a function called unique that kind of does that for you. So I actually want you to write the code. So I want you to use the standard library, but no unique, because that makes it one line of code, kind of. So are the integers inputted from the keyboard? They are. So read in integers. I can give you some starter code for that. All true. X equals read. I'm in Notepad, which is painful. Break, and then, I don't know, add it to a data structure of some sort here. I'll let you figure out what data structure you use, because that's part of the thing. Okay, I'm not going to tell you what data structure to store it in. Okay. So. This will start you off. I'll put it on. Can you give an example of no, stood, unique, or similar function? There's a function in the standard library called unique. You can't use it. That's what it means. You cannot use stood, unique, or similar function. All right. So I'm going to pause the recording now, and I will give you 15 minutes or so to do the assignment. While you're doing that, I'll just put all the grades for Shapes up onto Canvas, so you can take a look at it. Also, there is iBooks due on Wednesday, so I moved that back by 2 days for you because it wasn't, I think, visible on Canvas for some reason. So I moved that back to Wednesday. So how about it? Have some lab time. When we come back, paste your code, and we can take a look at it. All right. So yeah, we did a sea shanty workshop on Friday. And you might notice that I haven't posted the link for it. The reason for that is you have to message one of the scallywags that was at the workshop and ask them for a link. So don't wait till Thursday night to work on your extra credit. For the sea shanty workshop, you must message one of the crew of the pirate ship, even though sea shanties have nothing to do with pirates, more or less. So, work on Overwatch too. Overwatch, I only do the weird poses. So the question about I've been asked by a game company to do a soundtrack for them in sea shanties. So I went out on a lake yesterday. We're sea shantying around, we're rowing and singing and recording and stuff like that, and probably annoying any number of people who are just trying to enjoy a lazy Sunday afternoon. And it's funny, there's this party and there are all these 20-somethings like drinking and stuff like that, and we're like rowing past and they start shouting at us, and I thought, oh, they're mad or something, because we're like being loud. You can hear my voice is kind of shot right now. And I'm like, what? And the girl's like, take me with you. She's all drunk, and we're like, you want to go on a boat and sing sea shanties? She's like, yeah. And we're like, all right. So we start rowing over, and her friend's like, no, you can't go with the pirates. It's a bad idea. It's a bad life decision. And so by the time we kind of row up, we're like 20 or 30 feet away. She's like, my friends tell me I can't go with you, so sorry. And we're like, all right. And we row off singing and stuff like that. So probably the right move on her friend's part, not letting her go off with a bunch of pirates on a lake. But it was a compliment, because she was, I guess, enjoying our singing and stuff. So if you want to learn about sea shanties and stuff like that, again, you're gonna have to message one of the 5 students that came to the live recording. Okay, that's on the workshop channel. You can see their names there. I've locked down the workshop channel, so you're gonna have to message one of them for the link. Okay. Carry on. Okay, so we're back. So first question, and this is something that is kind of like the big thesis for CSI 41, is which data structure should you use? You're going to be inputting a bunch of numbers. You have to preserve order. You have to keep the order they're in, and so there's 3 data structures instead that you should use, or could use. Technically 5, I guess you could use. C-style array and C++ array. I wasn't counting those because they have a fixed size and you don't know how many times they're going to input a number, right? So I didn't count those, but technically there's 5 order preserving data structures where it writes down the order they come in. The 3 that I was thinking of was vector, dec, and list. So vector pushes and pops off the end. Seems pretty easy if you're going to build the data structure using a vector. You just grow it, the usual way. Dec, same thing. List, same thing. You can just call push back over and over again. And so that doesn't work, Cabrera, because you used a set. So it is not going to preserve the numbers in the order that you entered them. You will get lucky if you type them in sorted order, but if you use a set, then it destroys the order. So if somebody types in 420, it should return 420, right? Well, not the 0, I guess, at least the way that I did it. So you have to use either a vector or a list or a dec. Now, when we're erasing things out of the data structure, we're going to be erasing from the middle of a data structure. So between vector, list, and dec, which one of these should we prefer? So between list, dec, and vector, which one should we preserve? Which one should we use? These are the 3 that grow, that preserve order. Let me erase my thing, my solution from earlier, and we'll just take it to the top while true. X equals read, enter a number, 0 to quit. So we need to add it to a data structure. And so when you're in CSI 40, all you know is like a vector, so you're just like, I'll use a vector. And then when you search it for duplicates, at every point along the way, then you have to sweep through the whole array looking for any duplicates up to that point. And then if you delete it, then everything has to be shifted back 1, and that is an order n cubed algorithm. But we can do it not only in order n cubed time, we can do it in order n time, 2 whole steps faster, if we use the right data structure and the right algorithm to check for duplicates. So you can output the ints as they're inputted. You can check if, yeah, before it's adding it, you could. The notion I had was actually that you would be given a function, right? So you have to do a function called duplicate or something like that, and it needs to take something, right? So you're handed, right? You're given in integers, right? And so you can do it as you go along if you use a vector or a deck. The notion was you're handed a data structure and you need to remove duplicates from it. And so the right answer for that is a list. So we're going to use a list of integers named lit. I don't know. I don't like using L's because it looks like the number 1. Like I remember over the weekend, a student was like, I put in the number 1 here and it's not working. It's like, yeah, it's because it's an L, right? So it's never heard of the list. Okay, so let's include list, and we're going to make a list of integers named lit. So every time we read a number, we're going to say lit dot push back the number, and then we're going to call duplicate, passing in lit, and then we're going to say for every integer and lit output it. Okay. So this is. Are you mad at me? Why are you underlined? I don't know. Okay. So rather than worst case order in cubed, which is what we would get if we used a vector and just did a brute force search every time we went to the next element in the list, we can do it in order in time if we use a hash table. So we're going to use a hash table, unordered set. In this case, we don't need a map, named hash table. And what we're going to do is we are going to iterate through the list, and every time we find a duplicate, we delete it out of the list, and every time it's not a duplicate, we add it to the hash table, and then we can check to see if it's a duplicate later. Hash tables are great for looking for duplicates. So your solution would be to have both a vector and an ordered set. Check if the input of data is already in it. If it isn't, push into the vector. Yeah, but the notion is you're writing this function, right? This is your code. Your code goes here. Okay. So in order to do that, it's order in. All right. So here we go. So we are going to do a lit dot begin. We're going to do a type of for loop that you don't see me often use in this class, which is a iterator based for loop. We normally use a regular for loop for int I equals 0, I is less than 10, I plus plus. That's a regular for loop. Oftentimes you'll see me use a ranged for loop like this. Today I am going to be using an iterator based for loop, and the pattern for that, which I've talked about before briefly, looks like this. You start at the beginning, you go to the end. So you say for iterator is equal to begin, iterator is not equal to the end of the list, and that's a light. What's going on here? Okay. Weird. Okay. And that's it. Deliberately left blank here. And we need unordered set. That's what it's mad about. Okay. There we go. Good? All right, thank you. So we're going to have a pointer starting at the beginning of the linked list, and we're going to go one element at a time down the linked list. And you might say, wait, we don't have a go right thing, and you're right. We don't yet, but we will. So what we want to do is say, if we have a duplicate, erase it. And the reason why I'm doing this weird for loop here, I could do it like this, but this is the standard pattern, by the way, for a iterator for loop pattern. And it's probably worth learning this pattern. You'll see it all the time. It's very similar to the same patterns we use when we're iterating across a linked list for, the pointer starts at the head until it hits the bottom, blah, blah, blah. Very similar, except it uses iterators, which are like generalized notions of pointers. And so we want to see if the value here is in the hash table already. Is this a duplicate? Okay, and so the C++20 version of this is contains, so we can say if hash table contains the value pointed to by the iterator, then it's a duplicate. Okay, and if it's not a duplicate, then we'll do something else. Now, what we want to do is erase it. So we want to say erase let's just say erase the iterator here. Now, here's a problem. If we erase the iterator, we've deleted the thing pointed to by the iterator. Can we do this afterwards? Like we're going along, we find a duplicate, we delete it. Can we now say iterator plus plus? Can we use an iterator after we've deleted it? No. Can't de-increment it. Can't post-increment it. So we could do something like make a duplicate of the next or whatever, but as it turns out, erase returns an iterator pointing to the next element. So as it turns out, we can just say iterator equals erase iterator, and then that's why I didn't have something up there. But if we don't erase it, then we still need the iterator plus plus down here. It's kind of a weird pattern. But every time you delete something out of a data structure, you have to ask yourself, like, did that invalidate my iterator? You know? So this is the way. So you go through, and there's one other thing we have to do, which is to add to the hash table insert the value pointed to by the iterator. So so very, very nice little algorithm there that uses a hash table and a linked list together to do order in deduplication. While preserving order. The person who did it with a unordered, if you did it with a set, it would sort everything, which would destroy the order, right? And it would also be order in login, because you're doing every insert into a BST is login. You do n of them, it's n login. This is an order in, and so yeah, basically free. If you were doing it while you entered the data, then you can basically kind of do it as you go along, check for duplicate, add it to the vector if it's not in there already. But again, the idea of the assignment here is you're handed a data structure, and you need to remove duplicates while preserving order. So this is the fastest possible. Like you can't do faster than order in, because you have to look at every data element to know if it's a duplicate. All right. At least if you're handed the data in this format, where it's just random data, like you're just handed numbers, and you have to look at each one. And so a lot of people will actually say order in is free, right? Because if you look at Muya's way he did it, he just did it as he was doing the data entry, right? Like pretty much every algorithm is going to read data in, do some stuff, and then write it out. Like that's your big three phases of, some CS professors teach that is a program. You do input phase, analysis phase, and output phase. And if you do your analysis while you're doing the input in order one time, it's essentially free, because you've got to load all the data off disk, right? If you don't have to load it off disk, it's not input, right? So you got to read it in, you got to write it out, and if you can just kind of do it as you're doing that, then it's free essentially. So this is essentially a free operation. So order in is about as fast as you can go. Yeah. So if you use a BST, it would be order in log in. If you used an unordered set as you're going along, then it's order one checks for duplication. And the worst case would be order in cubed, right? Where you do something like this. Like if you're not using a hash table, then every time you go along, you check all the previous entries to see if there's a duplicate, right? So you do something like this, like if the value pointed to by the iterator is equal to the value pointed to by each previous not you. Okay. So as you go along, if you check all the previous values. So if you're at element 10, you check 0 through 9 to see if they're duplicate. You get to 11, check through 0 to 10. 12, it's 0 to 11. 13, 0 to 12. It's a order in squared algorithm. So if you have a match, then iterator equals erase iterator, else it plus plus. So here's a order in squared algorithm. And then if we weren't using a linked list and we were using a vector instead, a vector erase is order n instead of order 1, and this would be an order n cubed algorithm. Yay. Sad. Okay. Basically, if you have a black box that just told you exactly what the output was, how long would it be? Best case, we look at each element and determine whether it's a duplicate, it'd still be order n. So it can never be faster than order n. Yeah. You basically have to touch all the data, at least in this format. Like, in some data formats, like somebody might say, there are 1,000,000 fives. Then you don't have to read in 1,000,000 fives. You just say, there's a 5. Thanks for telling me about all the duplicates. Like, there's ways of formatting these things. But like in just this format where you're just entering random data, yeah, order n is the provably best time. Okay. So it can't be slower, so we actually call it theta n for a tighter bound. Yeah. But only nerds use omega and theta notation. So. It's true though. Like big O is the upper bound on running time, and that's usually all we care about. But you can sometimes come up with a lower bound on running time, and if the lower bound and the upper bound are the same, then it's an exact running time. Yeah, but big O is usually what we talk about, because we usually just care about worst case time. Like, what's the worst that can happen? We usually don't care about fastest. Okay. Yeah. Do you guys understand? This is order n squared, and then if I switched it with a vector, it'd be order n cubed. Right, so I'm gonna put it back the way it was before. And just leave the nice, pretty implementation on there. Okay. So the lower bound, yeah. Omega is the lower bound, and then theta is the precise. I think that's in your Zybook somewhere. But honestly, like, all you ever see, like in like documentation, right? CP reference, vector, pushback, complexity, amortized constant time. That's worst case, right? Like, it's just, in practice, yeah, sure, there's theta and omega, but like nobody's. And if you go heavier into theoretical computer science, yeah, sure, but okay. All right, you guys understand? That cool? A little warm up. All right, what we're going to talk about today is first of all, your next homework assignment is going to be called histogramming. Histogramming is going to be kind of similar to this. The notion is, rather than deleting duplicates, you're going to count duplicates. So your input is going to be a text file, and you're going to count how many times a letter appears in it. So for example, here I made an array of size 256. You guys know about ASCII, right? ASCII is the every time you type a letter in, you're not actually typing a letter. I mean, you kind of are, but like, you got a letter on your keyboard. But under the hood, it's just a number. So like the letter A is 65, letter B is 66, capital B is 66, lowercase is in the 90s, 97 for A, 98 for B, stuff like that. So whenever you type in a letter, it's just a number, and it's a number from 0 to 127, because ASCII is a 7-bit format, and so Unicode is kind of an extension of ASCII that uses the higher bit, and if you see that, the numbers can range from 0 to 55. So basically, in order to handle Unicode and extended ASCII and some other stuff, I'm making an array of size 256. And then what I'm doing is I'm reading one letter at a time, just kind of as a troll joke. If they type in a Q, it quits, so you can't have any Qs in Hamlet or whatever. But for your homework assignment, you have to just read till the end of the file. You know. And then here is the big brain thing for your homework assignment. Okay, so I'm reading in a character, right? And that character, like if they type in capital A, is 65. And so I'm going to bucket 65 and incrementing the count there by 1. Okay, this is a fixed size array. I'm using an array instead of a vector because it is fixed size and it's small. So array is in fact the right data structure to use there. You could use a C style array if you're dumb. If you want to. There's no benefit to a C style array, but if you wanted to, you could, I guess. This code here, 0 fills it, so the whole array is initialized to zeros. And then every time we read a letter in, we increment the count at that bucket by 1. This is actually a hash table, kind of, right? So we hash to a location. It's perfect hashing, right? We have 1 bucket for every possible letter in ASCII. We hash there, and we increment the value by 1. We have 1 bucket per possible ASCII code, and then some, because there's these things called extended ASCII that have like the angle characters and things like that to draw windows and text and stuff like that. So, Muya is running through big theta and things like that on chat. Amortized time, yeah, is average time. If you average it out over a large number of operations, what is the average time? So, for example, vector pushback is, on average, it will be constant running time. Because you double the size of it every time. It doesn't have to be double, but you double the size of the vector every time you run out of room. And so you only have to do that operation 1 out of every so often, and it does this much work, and you divide the 1 by the 1, and you get the thing, and you get a 1. So it averages out to constant running time. In practice, though, you will see lag spikes. So as your vector is growing, you'll see these ever-increasing spikes in time where it is making a new vector and copying all the values over. And so if you know what you're doing, you reserve size in advance in your vector. You call vector.reserve. And if you just have an idea that you're going to have 1,000,000 elements, you say vector.reserve 1,000,000. And if you go over, it's not a big deal. This dot size doesn't change. It's just internally dot reserve is used for internally allocating the array that the vector has. So you can use dot reserve if you have an idea of how much space you need. So that's vector. It's back, and you say vector dot reserve 1,000,000 like that. And if you see out like vector dot size, this will still tell you 0 because there's no actual elements in the vector. But internally, in its secret of secret hearts, it has a 1,000,000 ints already allocated. Probably. I think it can actually ignore that if it wants to. Yeah. So you can see the vector says, I don't have any ints in me. But secretly, it has 4 megs allocated, or so, somewhere in there. I think it can ignore that, but it's kind of a good clue to the data structure. Like, this is about what we expect to need. Use a C-style array if you're quite good with size. Yeah. Okay. So, for Ramidit, you're a fan of cache locality. Yeah. So, okay. So, you're going to count how many letters, right? So if we call the code and run it, A, B, 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 C, 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 D, F, Q. Okay. And so it's, this thing is actually printing the entire thing, right? So I got no null characters, I got no tab characters, I got no new lines. We go through here, we got 3 A's, 3 B's, 34 C's, and a D and an E and an F. Okay. That makes sense? And so what I'm doing here is I'm converting from a number to the ASCII equivalent, right? So I'm going the other way on ASCII. With here, what I'm doing is I'm treating the ASCII code as an integer and using that as an index in an array, and I'm making sure to use an unsigned integer here. I could have used an unsigned char if I wanted to type more. But I don't want to use a char. I want to use a uint8 just in case my chars happen to be bigger than 8 bits, which can happen. So again, anytime you are reliant upon the number of bits, 2 to the 8th power is 256. I'm reliant on it. You need to fix your type, your sizes using a fixed size type. So so here I'm reading in an ASCII code essentially, using that ASCII code as the bucket in a hash table and incrementing it. And then here I am printing out, I'm converting from a integer to a char, which will print out the ASCII equivalent of each thing. If I wanted to, I could only print the things that are in there. If count. Hello. And so I got 2 exclamation marks, 1 H, 1 E, 10 L's, 1 O. Okay. So that's your homework assignment. It's due Friday. It's kind of half done for you already. The second half of the assignment you didn't do last semester. That's why I'm kind of giving you this starter code here, because last semester students kind of did a histogram assignment already. For the second half of it, what you have to do is you have to sort the output here by count. So it would print out the L's first because there were 10 of them. Then it would print out the exclamation marks because there were 2 of them, and then the rest in alphabetical order. So I would do that by making a histogram class, or maybe just a character class, and having maybe just like a character and a count or something like that, and then writing my own like operator less than, or making a lambda or some other sort function and sorting my vector array or whatever using the tool operator less. Vector. That. And then you'll be able to sort your array or vector or whatever you use to hold the data by count rather than by character. Okay. So go ahead and get working on that, I guess. See if there's something else I talked about. Oh, yeah. Right. I do actually have a little bit of lecture for you. That's nice. Right. Okay, so up till now we've been kind of focusing on one data structure at a time. And when you get into bigger projects and more complicated assignments and things like that, what you'll find is you end up using multiple data structures together. It's very natural, right? And so when you started in CSI 40, like you just kind of put everything into main, and like if I had you like do that unique deletion thing earlier, you'd probably make a vector and then iterate through the vector and erase things out of it. And you kind of have to, maybe you don't know how to maybe you don't even know that vector erase exists, so you write your own erase function, and you have a for loop inside of a for loop inside of a for loop, and your brain's going like, I can't keep track of all these loops, there are loops inside of loops inside of loops, and it's horribly inefficient, and it's buggy, and stuff like that. And then after you take CSI 41, you sort of elevate your game, right? So rather than doing like a loop inside of a loop inside of a loop, you were like, I'm going to use a hash table. And then I'm going to use a linked list and use std functions. So rather than calling erase, instead of writing erase yourself, which would be a for loop in a vector, or all this pointer stuff if you're in a linked list, you just call erase and it just does it for you. And so you elevate your mind, you elevate your game. And if I had to write that whole thing from scratch, I would have had to write my own hash table, I'd have to write my own linked list, and I'd be sitting there for like an hour, like writing all this stuff out and testing it, and the job interviewer is like, are you even going to start on the unique deduplication thing yet, or what's going on here? And I'm like, hey, Gon, I need a hash table. And it's like, you stood, unordered set. So when you take CSI 41, you're aware of what data structures exist. You learn when to use them. And you begin thinking about them at a higher level. And so I'm just going to drop a hash table in here. I'm going to call insert in the hash table, and I'm going to check to see if the hash table has the thing in it. Nowhere in there did I need to write a hash table or even know what kind of hashing it's doing or any of that stuff. I'm just stepping up at a higher and higher altitude. Just be like, hash table, insert, search. Okay, it works. Beautiful, right? And then when you take CSI 26, you elevate again, and you start thinking about things in terms of algorithms, right? Oh, I'll just throw Dijkstra's in here. That sounds like a shortest path question. I'll just Dijkstra's it, And then you elevate again, and you're your head's up in the clouds, and you can just gaze down at the mere mortals below. It's such a high level. Just sprinkle a little A star in here and do some higher level pathfinding, And then in CSI 45, you go in the opposite direction. So in CSI 45, instead of going up into the clouds, you go down into the dirt, and you learn about how the CPU works and how registers work and clocks, and you wire things and solder things and stuff like that. So just casually throws a Dijkstra's at. Yeah, because after you've done enough times Betancourt, you can just be like, Dijkstra's, and you just sprinkle little Dijkstra's onto a problem and you solve it. It's easy. It's not a big deal anymore. So, your eyes are burning. All right, let's see if I can soften it a little bit. Weird. Why is that not? Oh. It's only changing the... There, do that one. There. Do most interviewers want you to use STL structures? It depends on the interviewer. Remember, a lot of people don't know the STL very well. And so if they don't know it, they get mad if you know it because it feels like cheating, right? Linked lists in the STL have a .unique method on them. So all you have to do is build the list and then call .unique on it. It just does all that for you. It's one line of code. So I had a student do that in the previous class, and so for this one I said, you can't use unique. And that's kind of what job interview question oftentimes are like, is that there's a certain level, not too high level, not too low level. They just want to see if you can think through how to remove duplicates, and they don't want to see you down in the weeds making a hash table and linked list. They don't want to see you up here just be like .unique, done. Sometimes they do, and oftentimes you can just be like list.unique, and they're like, thank you, good answer. So it just depends. Okay, so it just depends on the interviewer, and so you always ask, because if nothing else, asking makes you look good. I am aware that there is a solution for this already in the standard library. I would like to use it. No, you can't use it. Okay, but now they know that you know the standard library pretty well, and that's one of the things they want to hire for, because then you're not going to waste their time in production, rewriting stuff that's in STD. So, my point is that as you develop, you start gluing together multiple data structures, right? So when I made a hash table for you guys in 3 lines or whatever it was, basically insert was 1 line, search was 1 line, delete was one line, because my hash table with chaining was a array or a vector of binary search trees. So each bucket in the hash table was a BST. And so that's a composite data structure. It's a hash table of BSTs. And I would just hash to the right bucket and call .insert on the BST there, and it handles it for you, right? Standard library uses chaining with linked lists. I did chaining with BSTs. Functionally, the same thing. Okay. You can make arguments about which is better, but it doesn't really matter. So it's just an implementation detail. So anyhow, so that's, you can almost think of it as like Tinker Toys. You've got something that works and you just attach it to another thing, and you put 10 of those into 10 different boxes, and it really allows you to sort of elevate your game. That's really what CSI 41 is about. It's about leveling up and moving your head up into the clouds and getting away from the tedious details of doing things like this pointer points at this thing and this pointer points at the previous, and if it's null, then it doesn't. I don't write code like that in practice. I just use standard library stuff. And if the standard library is deficient, then I either make my own by using the components of the standard library, or I find it in Boost or something like that. There's plenty of libraries out there that do like Bloom tables and stuff like that, Bloom maps, Bloom filters, stuff like that. There's all sorts of interesting data structures out there. Are enums data structures? Not really, because they don't hold data. Enums are just a list of constants. It's just a list of like associating names with numbers, basically. Okay, so yeah. All right, so yeah. So I was going through some of my old code, and the compiler that I wrote back in college used a stack and a queue in concert with each other to go through stuff. If you think about how undo and redo work in Microsoft Word, every time you take an action, like you select a paragraph and you bold it, then that gets saved onto the undo stack, right? And if you hit undo, it comes off the undo stack and it undoes the operation. So think about how wild that is. Everything that you do has to be saved and has to be reversible. It's kind of wild, right? And then you keep doing things. You bold it, you set it to 22-point font, change the font. Each time you change the point size, change the font, change the color. And then you might go undo, 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 undo. And as things are undoing, they get popped off the undo stack and they get pushed onto the redo stack. They're like, oh, went too far, Control Y, Control Y, Control Y, and then things come off the redo stack and go back onto the undo stack. And you can sit there and flip back and forth between them, undo, 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 redo, 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 as much as you want, and it pops off one stack and pushes onto the other. And then once it's where you like it, you start typing again, the redo stack gets cleared, and the new operations go onto the undo stack. Just two data structures, but it's very cool. It's very cool if you think about it. Show it seen copied for the 45. It won't help you with a 45 compiler assignment. The 45 compiler assignment isn't using proper compiler design. It's just completely straightforward. You read a line of code and you output the assembly for it. And you just go line at a time. Whereas real compilers have parse trees and are far more complicated than that. All right, so yeah. Okay, so yeah, basically the goal of this class is to have you understand when you use each of the fundamental data structures, like linked lists were the right answer for today, right? For the warm-up assignment today. If you used any other data structure, it would have been order n squared. By making it a linked list, it's order n. And also using a hash table to check for duplicates was the right data structure as well. That turned, that gave you also an n squared to n, like it clicked you up one level of performance. So the worst case CSI 40 solution would have been order n cubed. We got it up to order n. So two whole, steps better performance, which is mammoth, right? So like if you were doing that with a million numbers, my code would run in a million steps, give or take. And a CSI 40 assignment would run in a million times a million times a million steps. Right? So, quite a lot faster. Right? It'd be a trillion times faster for just a million numbers, which isn't even that many numbers. Okay. So let's do a couple quizzes with you guys. Masood, are you here? Taha Masood. Let's see who's here and who's AFK. Is Masood here? Excellent. Give me an example, Masood, of when you would use a deque, a double-ended queue. DEQUEUE. And Shook, give me an example of when you would use a int as a data structure. And Holman, give me an example of when you would use a linked list, not the one we did today. And Portnov, give me an example of when you'd use a hash table. Again, not the example from today. And Hernandez, give me an example of when you would use a array. Yeah, int as a data structure. Right? And Lopez, give me an example of when you would use a stack. And Boyles, give me an example of when you'd use a queue. Hash table phone numbers, How would you use it for phone numbers? And Megia, give me an example of when you would use a vector. And Hesterberg, give me an example of when you'd use a BST. If you want to order one combination of two data sets, yeah, that's a good one. That's a good one. Merging things is nice with linked lists, for sure. And Mincarelli, give me an example of when you'd use a Bloom filter. And Otal, give me an example of when you'd use a C-style array. And Romero, give me an example of when you'd use a C++ style array. And you always use a vector. Yeah. The BST can hold the key to encrypted data. Not sure when to use an int? It's a bit field. Ints are bit fields. If you want to pass 32 options to a function, each bit in the integer represents an option that's on or an option that's off. And so rather than having 32 different parameters, up to 32 parameters, you don't have to use all of them. You pass in an int, and each bit in the int is, this is true, this is false. Vectors have cache locality? Yeah, so the best data structures for cache locality are vectors and arrays, right? Because they're all contiguous in memory. And so things that are next to each other in memory tend to be faster. You'll learn about that in CSI 45, but it is definitely a benefit to arrays and vectors. Decks have worse cache locality than arrays and vectors, for sure. Cabrera, give me an example of when you'd use the stack. Linus, give me an example of when you'd use a queue. Stack insert things into proper order to pop it out backwards. Yeah, reversing things are very common using stacks. Sure. Yep, last in, first out. If you want to do palindrome detection, stack. Sure. Can you get a redemption question, Shook? Yes. Give me an example of when you would use... I think we've gone over all of them, haven't we? Unordered map versus unordered set. Use an array when you don't plan for the size of the container to change. Yeah, it's true. And it's small. Remember, arrays are stack allocated, and so if you have a large array, you'll run out of stack space, you'll stack overflow, and everything dies. So you have to be very careful when using arrays to not have them be too big. You can easily make a vector of, you know, 1,000,000 ints. It's like, whatever, it's not a big deal. But if you do that in a C-style array, it depends on your stack size, right? 4 megs of stack space is, do you have 4 megs of stack space? I don't know. CPP arrays can be used when you don't feel like using a vector. I don't know. Usually vectors are just kind of easier to use. Having a fixed size is kind of annoying, and having to worry about stack overflowing is also kind of annoying. Like I prefer not to think about it. CPP arrays are more of an optimization, right? So you use an array instead of a vector when you want better running time. That's basically what it comes down to. And I don't know if you would encounter enough of a difference to even make it worthwhile, to be perfectly frank. But maybe you would. I don't know. If you're in the situation where you're like in high frequency trading or something like that, then yeah, you want to squeeze every bit of performance out of it. Oftentimes an array is going to be faster than a vector because stack allocation is faster than heap allocation. Also, sometimes you want to have uninitialized variables, and vectors always initialize themselves because they're nice like that, but it's also slow. So, an error map, you could see. An error map could be when you want to hash strings by their key. An ordered set could be hashing a set of ints. Sure, yeah. Exactly, that's the difference between a map and a set, sure. You use a CSL array when you want no bounds checking. Yeah, if you wanna, yeah, that's funny. All right. All right. When should we use a queue? I don't think anyone answered that question. When should we use a queue? In which should we use a BST? Is there a situation where you should ever use a C-style array? I can't think of one. If you're writing C, you know, writing C, use a C-style array. If you're working for a company that is stuck in the 80s and 90s, okay. When you want pop front only, yeah, a queue is used when you push back and pop front, and you really want to enforce that restriction. I basically never use a queue. I would just use a deck and push at the back and pop off the front. And the reason for that is because a deck you can print all the contents of it, and a lot of times I want to see what, like when I'm debugging, I want to see everything in it, you know. And a queue, you can't do that. You can only see the first element, last element, and you know. Why use a deck instead of a vector? Use a deck when you need to push and pop at the front, as well as the back, in order one time. So if you're implementing like a line for a bank, then people arrive at the back and they pop off the front, and that sounds a lot like a queue to me, and it is, but I don't use a queue, I use a deck. The reason for that being, decks have more functionality. A queue is literally a deck that they removed functionality from. So I just use a deck and just push at the back and pop off the front. Just call it a day. So that's when you use a deck. If you need to push and pop off the front, use a deck. If you don't, use a vector. Vectors are 30% faster than decks in practice. So, queue for ordering a burger at a restaurant and getting an order number. Yeah, sure. If decks were faster, would you pick them over vectors? Yeah, if decks were faster than vectors, there'd be no reason to use a vector. It'd be like C-style arrays. There's really no reason to use a C-style array. Backwards compatibility, working with old compilers, sure. But like in modern C++ and you're writing the code yourself and you don't have to worry about interoperating with other people, there's zero reason to use a C-style array. Just use a C++ array. If you want array, the fixed size, stack allocation. Most of the time, though, I just start with a vector, and if I need the speed, I can make it an array. Or if I know that it's fixed size and small, I might just use an array. Because, you know, like for the histogram, it's 256 buckets. It's fixed size. It's not large. It's a K of RAM. You know, it's not going to break the bank. I'm not going to stack overflow. So I just made it an array. It seems like the right tool for the job, you know. But yeah, if decks were faster than vectors, then there would be no reason for a vector. I'd just use a deck for everything, right? But they're like 30% slower. The last time I benchmarked it, they're a bit slower. Unless you need to push and pop at the front, in which case they're much faster. All right. So yeah, that's basically it for today. Just a little review of the data structures and work on the histogramming. Basically, it'll test your ability to, I don't know, make like an operator minus or something. Like I've mostly given it to you. So, yeah, this was a CSI 40 assignment, so it's just gonna be a little 5-pointer, you know, because I've pretty much given you the answer. So just a little easy 5-point pickup due on Friday. It's called Histogram on the server, and I'll put it up on Canvas in a second. What is a forward list? A forward list is a singly linked list, and so forward lists are kind of dumb also. Like there's kind of no, like if you don't want to go backwards, you know, use a forward list. Depending on how they're implemented, they can take up less RAM. That's kind of the benefit, I guess. Doubly linked lists oftentimes will have 2 pointers. A forward list only has 1 pointer. So there you go. But there's a lot of algorithms that just don't work on a forward list. So you can't call. There's a lot of functions, a lot of standard library functions that just don't work with forward lists. They work with lists, they don't work with forward lists. And so I basically, you know, don't see any use for them, pretty much. Okay, so that is it for today. Get cracking on histogram, and then we will continue this slide on Wednesday. All right, peace out, everyone.